Another thing that is going to become important that we've talked about before is position vectors. So imagine this is your three-dimensional space, okay, where this vector is coming out, X, Y, Z. And imagine you have this vector, call it A. And then you have this vector, let's call it B. And then you have another vector somewhere far away, like C. How do you define these vectors? Well, A is easy. Suppose this is 3 and 2. Actually, if I'm doing it in 3 dimensions, I'm going to write it like this. 0, 3, 2. What does that tell you? Its X is 0, its Y is 3, and its Z is 2. Yes? If I look at my vector B, and it's in 3 dimensions, and I write this as 1, 2, 4, what does that tell you? Yes, Casey?
The X is in 1, the Y is in 2, and the Z is in 4.
Good. X is 1, Y is 2, and Z is 4, right? Now look at C. How do you define C?
The weird kid in the corner.
The weird kid in the corner. Good. But we have to define that weird kid in the corner. We call vectors like these separation vectors. And what that means is that we have to define where its tail is, and we have to define where its head is. Okay? So I'm going to redraw vector C, that weird kid in the corner. Okay? And so now that weird kid in the corner, I have to define its tail and its head. And how do I do that? Well, the way I would do that is I will have to define a vector that goes from the origin to its tail and from the origin to its head. This is the vector that Griffiths calls that funny looking R that you see it all over the place. It's not complicated once you actually understand what Griffiths is trying to say. And in this case, when you define the vector, it's going to be defined as, pick 3 numbers, guys.
7, 6, and 2.
7, 6, and 2. Okay, now pick something, all 3 numbers bigger than this.
9,
14, 8, and
9, 10, 11.
Okay, 9. So now these are the 2 vectors that correspond to the tail and the head of the vector C that I had. So now in order for me to define what C is, what do I have to do? That R vector will just be 14 minus 7i plus 8 minus 6j plus 9 minus 2k. Make sense? So what is this funny looking R vector? 7i plus 2j plus 7k. And that is what Griffiths calls a separation vector. People tend to make this way more complicated than it is. It's actually quite simple. Did you see the progression of it?
Yeah. I just came up with like a little like thing in my head. With
Yeah.
the weird kid in the corner thing.
Okay.
It's the weird kid in the corner, and he needs friends to like connect him to the real world.
Connect him to the origin.
Yeah.
There you go. That is actually a really good point.
Thanks.
Remember that for the rest of our lives. Okay, so this is what the separation vector is, and I think Griffith defines it as R minus R prime. And I think he calls it like this. And correct me if I'm wrong, you guys. And he calls it R hat, R prime. One of them is prime and one of them is not. I think he calls them the source point and the field point. So he calls this point the source point, and this one he calls it the field point. And the field point is what he calls where you are calculating your E or B fields, electric or magnetic fields. And the source point is where the charge is located. But as Casey said, this is the weird kid in the corner, right? With the source and the field. That's a good analogy. That's all that it is that weird kid in the corner.